Right, so the topic of discussion for now, it is what we refer to as the clearance volume, simply meaning we are now accounting for or considering or taking into consideration what is known as the clearance volume. This is the volume that remains in the cylinder after the piston has reached the end of the compression stroke. That is referred to as your clearance volume. This is the volume that remains in the cylinder after the piston has reached the end of the compression stroke. Okay, right. So let's quickly refer to this graph. Okay, right over here we have a graph, otherwise referred to as a diagram, a PV diagram, a pressure versus volume diagram. Okay, right. Now from point 2 to 3, okay, there's point 2 to point 3. Okay, from point 2 to 3, compressed air is delivered from the cylinder, simply meaning compressed air, meaning the air has been what? Compressed, and now it is delivered from the cylinder. But at 3, okay, the piston has reached the end of its stroke, and so delivery of air stops at 3. Simply meaning no air is no longer delivered at 3 in terms of stroke wise. Okay, now V3, when we say V3, we are referring to volume at point 3. Okay, V3 is the clearance volume and it is filled with compressed air. Okay, compressed air, right? Our clearance volume is at point 3 filled with compressed air. Okay, right now as the piston starts its intake stroke, as the piston starts its intake stroke, it's now going to start its intake stroke. Intake simply meaning is now going to suck air in. The residual compressed air, residual means leftover air, the residual compressed air expands according to the law PV to the power of N, which equates into a constant C, and it is not until the pressure is reduced to intake pressure at point 4 now that the inlet valve will begin to open. Okay, so simply meaning there's something happening between point 3 and point 4. The residual compressed air expands according to the law PV to the power of N, which equates into a constant C, and it is not until the pressure is reduced, it's not until the pressure is reduced, okay, to intake pressure at point 4. Simply meaning when we are at point 4, we are referring to that as intake pressure. Okay, so we have a reduction. Okay, a reduction, right? Now as the piston starts its intake stroke, the residual compressed air expands. Okay, as the piston starts its intake stroke, meaning it's now sucking air in, the residual compressed air in our clearance volume, it now expands according to the law PV to the power of N equates into C, and it is not until the pressure is reduced to intake pressure at point 4 that the inlet valve will begin to open. The fresh charge of air, okay, the fresh charge of air between V1 and V4, it is called the effective swept volume. Effective swept volume. Okay. Okay, so now as we continue now, this refers to the volumetric efficiency, simply meaning it's a ratio of V1 minus V4 over V1 minus V3, V1 minus V3. Okay, so V1 minus V4, it is referred to as the effective swept volume, and then obviously from V1 to V3, that is referred to as your swept volume. Okay, Then also, if we go deeper, we will notice there's also what is referred to as a clearance ratio. Clearance ratio, it's basically clearance volume divided by swept volume. Clearance volume divided by swept volume. Now, when we say clearance volume, we are referring to V3. And then when we refer to swept volume, we are referring to V1 minus V3. Okay. So when we look at this graph here, what we notice now is that our external delivery or receiver pressure, this is where we will find that region, okay? And then we have our atmospheric pressure. This is the region of the atmospheric pressure. And then over here, this indicates to us the intake depression, okay? And then this here refers to our valve bounds. Now, the actual PV diagram is indicated here. It shows the effects at inlet and delivery of a gas, inertia and turbulence. The two shaded areas, negative work areas, are in addition to the theoretical area.